Every few minutes, a satellite crosses over the South Atlantic, and every few minutes, something goes wrong. A sensor glitches, a memory chip flips a bit, a camera produces a corrupted image. Engineers at the European Space Agency have a name for the region where this happens. They call it the South Atlantic Anomaly. It stretches from the coast of Brazil to the southern tip of Africa, and it is the single largest weak spot in the only thing standing between you and the radiation of deep space, Earth's magnetic shield. That shield has a hole, and the hole just got bigger. After analyzing 11 years of continuous satellite data, a team led by Professor Chris Finlay at the Technical University of Denmark published findings that stopped the geophysics community cold. The South Atlantic anomaly has expanded by an area nearly half the size of continental Europe since 2014. 2 million square miles of additional weakness carved into the invisible armor that protects every living thing on this planet. And since 2020, the rate of weakening has accelerated. The hole isn't just growing, it's growing faster. But here's the part nobody expected. The anomaly isn't behaving like a single defect, it's splitting. Finlay's team discovered that the eastern edge of the anomaly, the part reaching toward Africa, is weakening at 3 times the rate of the western edge near South America. Between 2018 and 2025, the eastern minimum lost roughly 600 nanotesla of magnetic field strength. The western minimum lost 200. Something beneath the South Atlantic is pulling the magnetic field apart from 2 directions at once, and the cause is buried 2,000 miles below your feet, at the boundary where Earth's solid mantle meets its churning liquid outer core. Picture what's happening down there. Earth's magnetic field is generated by the motion of molten iron in the outer core, a process called the geodynamo. Normally, magnetic field lines rise out of the core in the southern hemisphere and loop back down in the northern hemisphere, creating the invisible bubble that deflects solar radiation. But beneath the South Atlantic anomaly, the Swarm satellites detected something that shouldn't be happening. The magnetic field lines are diving back into the core instead of coming out. Finlay called them reverse flux patches. They're regions where the normal flow of Earth's magnetic engine is running backward, and one of those patches is moving westward across Africa, dragging the anomaly with it. Now zoom out. The South Atlantic anomaly isn't the only thing changing. Over the past 2 centuries, Earth's magnetic field as a whole has weakened by roughly 10%. The North Magnetic Pole, which sat over the Canadian Arctic for most of recorded history, has been migrating towards Siberia at an accelerating rate. It's moved so far and so fast that the World Magnetic Model, the system that underpins every compass, every GPS device, and every aviation navigation chart on the planet, had to be updated ahead of schedule, twice. So is this the beginning of a magnetic reversal? The question sounds dramatic. It is dramatic. Earth's magnetic poles have flipped hundreds of times in the planet's history. Geologists can see it in the rock. When lava solidifies, it locks in the direction of the magnetic field at that moment. Layer after layer of volcanic rock tells the story of a field that periodically collapses, wanders, and rebuilds itself, pointing the other direction. The last full reversal happened 780,000 years ago. On average, they occur roughly every million years. We're overdue. But here's where honesty matters more than drama. The researchers behind the Swarm study were explicit. They did not find evidence of an imminent reversal. The weakening they measured is real. The acceleration is real. The reverse flux patches are real. But a full reversal takes thousands of years to complete, and what we're seeing now could just as easily be a temporary excursion, a period where the field wobbles and weakens but eventually recovers without flipping. Nobody knows which one we're in. Not yet. What we do know is what happens when the field weakens, even without a reversal. Start with satellites. The South Atlantic anomaly is already the most dangerous region in low Earth orbit for spacecraft. With less magnetic shielding, more high-energy particles from the sun penetrate to satellite altitude. Memory chips get hit by cosmic rays that flip 1s to 0s, corrupting data mid-transmission. Solar panels degrade faster under the constant particle bombardment. Cameras produce streaks and noise in images. The Hubble Space Telescope switches to safe mode every time it passes through the anomaly, shutting down its instruments entirely to protect them. The International Space Station's radiation monitors spike every crossing. Astronauts on board receive measurably higher radiation doses during those minutes overhead. NASA's fleet of climate satellites, Aqua, Terra, and Aura, have been forced to perform dozens of protective shutdowns while transiting the region, sometimes corrupting the very climate data they were designed to collect. As the anomaly grows, more satellites spend more of each orbit inside the danger zone, and more of the data we depend on comes back damaged. Now think about what those satellites do for you. Weather forecasting, GPS navigation, communications, banking, agriculture, all of it runs through hardware that is increasingly exposed to a hazard that is measurably getting worse. Then consider what happens on the ground during a major solar storm. In March 1989, a geomagnetic storm knocked out power to 6 million people in Quebec for 9 hours. Transformers overheated, voltage regulators tripped in sequence across the grid. The entire Hydro-Quebec system collapsed in 90 seconds. That happened with a fully functional magnetic field. The storm wasn't unusually powerful by historical standards. The field just couldn't absorb all of it. Now imagine the same storm hitting Earth after another century of 10% per century weakening. The field that stopped most of the 1989 storm would stop less of the next one, and the next one, and the one after that. Each percentage point of weakening lets more energy through to the surface, to the power lines, to the transformers we can't replace fast enough. The economic stakes aren't abstract either. Studies estimate that widespread blackouts from geomagnetic storms could cost tens of billions of dollars per day, not per event, per day, and that's under current field strength. Every percentage point the field loses makes the math worse. There's another dimension to this that doesn't involve technology at all. Hundreds of species use Earth's magnetic field to navigate. Birds, sea turtles, salmon, whales. They carry biological compasses, magnetite crystals in their cells that align with the field and tell them which direction is home. When the field weakens or shifts, their maps stop working. Scientists have documented cases of mass whale strandings correlating with periods of geomagnetic disturbance. The connection isn't fully proven, but the pattern keeps showing up. Here's what connects all of this. The South Atlantic anomaly is not some exotic geological curiosity happening on the other side of the planet. It's a symptom. The magnetic field is a dynamic system driven by forces we can barely model, generated by currents of liquid iron moving at speeds we can only estimate, shaped by interactions at a boundary we've never directly observed. We monitor it with 3 satellites, 3 for the entire planet. And what those 3 satellites have told us over the past 11 years is that the system is changing in ways that are both measurable and unpredictable. The good news is that the Swarm mission has given scientists the most detailed view of Earth's magnetic field ever recorded. For the first time, they can separate the contributions from the core, the crust, the oceans, and the ionosphere. They can track individual flux patches as they migrate beneath the surface. They can measure changes year by year, sometimes month by month. We're not blind. We have the best instruments humanity has ever built pointed directly at this problem. The bad news is that the instruments are showing us something we don't fully understand. A hole in Earth's armor that's growing, a field that's weakening unevenly, magnetic structures in the core that are behaving in ways the models didn't predict, and a civilization that has become completely dependent on the very technologies most vulnerable to what happens next. 780,000 years since the last reversal. A 10% decline over 2 centuries. An anomaly that's doubled in a decade, and a liquid iron engine 2,000 miles below us that answers to no one. The magnetic field isn't going to vanish overnight, but it doesn't have to. It just has to weaken enough, at the wrong time, during the wrong solar storm, for the consequences to be felt by everyone. And the data says it's heading in that direction. So here's the question I keep coming back to. We spend billions defending against asteroids we might never see. We build early warning systems for earthquakes and tsunamis, but how much are we investing in understanding the one shield that protects everything? Because right now, that shield has a hole, and the hole is growing, and nobody has a plan to fix it. Because you can't fix something that's 2,000 miles underground. What do you think is the bigger threat to modern civilization? A solar storm hitting a weakened magnetic field, or an asteroid we don't see coming? I've been thinking about this a lot. I'd like to hear your answer.